Now let's dwell on a very interesting application of the Ohm's law, which is the Wheatstones Bridge. So the Wheatstones Bridge basically has four resistances that are arranged in this diamond-like shape. I've called the four resistances as R1, R2, R3, and R4. And what we'll do is to connect a source of power supply across two of the ends, in this case between A and C, and between the other two ends B and D, I'm going to connect a galvanometer. A galvanometer basically measures current flow, so it will detect any amount of current that flows between these 2 points B and D. So right now, my current starts to flow from this positive source of power supply, and at junction A, it can flow either up and down, or down and up, this way, or that way. And I'm going to call this current along R1 as I1. Along R2, we'll call the current as I2. For R3, it's I3. This is I4. And the current along BD will be IBD. Now, what would happen if the current flow through my galvanometer is zero? What can we say about points B and D? If there's no flow of current between 2 points, then those 2 points must be at the exact same potential, right? Because even if a slight potential difference exists between 2 points, it will cause some current flow. So when the current through BD is zero, the potential across BD is also zero. So when B and D are at the same voltage, what can we say about the voltage difference across AB and AD? At one end, A is the common point, and at the other end, B and D are at the same potential. So when B and D are at the same voltage, VAB must be equal to VAD, right? And if we were to express this using our V is equal to IR relationship, I1 times R1, which is VAB, will be equal to I3 times R3, which is VAD. In just the same way, if B and D are at the same potential, what can you say about the potential difference along BC and DC? Well, again, they'll be exactly the same, as one end C is at a common point and the other end B and D are at the same voltage. Therefore, VBC will be equal to VDC. Or I2 times R2, which is the voltage drop along BC, will be equal to I4 times R4, which is the voltage drop along DC. So when there's no current along BD, whatever current flows through AB must flow through BC, as there's nowhere else for it to go. Also, whatever current flows through AD has to flow through DC, as we won't have any flow between D and B. So my current I2 must be equal to I1, and my current I3 will be equal to I4. So if I take the two equations we used earlier, I can replace the I2 in the second equation with I1 and the I4 with I3. So my two equations are I1 times R1 is equal to I3 times R3, and I1 times R2, I've replaced my I2 with I1, is equal to I3 times R4. So we'll call this equation 1 and this equation 2. And what we ultimately want to do is to end up in a relationship that doesn't really have any of these current terms, but just the resistances. So how do we get rid of our I terms? If you look at these two equations closely, there is an I1 term common on the left-hand side and an I3 term common on the right-hand side. So if I were to divide the first equation by the second equation, I could get rid of my current. So 1 divided by 2 gives me I1 times R1 over I1 times R2, which will be equal to I3 times R3 over I4 times R4. And if you were to cancel out the I1s from the left-hand side of the equation and the I3s from the right-hand side, we end up with this equation. R1 over R2 is equal to R3 over R4. This is the balance condition, which happens when there's no current flow through the galvanometer. And this relationship is extremely useful in calculating unknown resistances. Suppose I have an unknown resistance R1. I can just group it up with 3 other known resistances in my Wheatstones bridge and alter their values until a balance condition is reached. Then my R1 would be equal to R2 into R3 over R4. But come to think of it, this might be a slightly tedious and impractical way to calculate an unknown resistance because there's so much of trial and error involved. That's the reason why the meter bridge was invented. The meter bridge applies the same concept as the Wheatstones bridge, but is a more practical way to find unknown resistances. To draw a meter bridge circuit, we take our Wheatstones bridge network and erase the bottom portion. And I'm going to replace this with a simple flint of wire like this. I'm going to shift this point A down here and point C down here. It makes no difference as they're all part of the same piece of wire anyway. Now if you look at this piece of wire AD, what is it essentially? It's basically a conductor of electricity, and any conductor offers some resistance to current flow, right? So my wire AD will also have some resistance associated with it, and I'm going to call this resistance as R3. And similarly, my wire DC, which is also a conductor of electricity, will have some resistance associated with it, and we'll call it R4. Now what do we know about the resistance of a wire? We know that it's proportional to the length. So this R3 out here will be proportional to the length AD. If you recall, the resistance of any wire or conductor is given by this relation. R is equal to rho times L over A. So I can write my R3 as equal to K times AD, where K will be nothing but rho over A. Similarly, the resistance R4 will be proportional to the length of the wire DC. Or my R4 will be equal to K times DC. If you notice, I'm using the same K term for R4 as was used for R3. That is because AD and DC are part of the same piece of wire, and hence their cross-section and resistivity values must be exactly the same. So what we do in our meter bridge is to keep adjusting the position D of the galvanometer along the wire AC until there's no current flow through BD. When no current flows through BD, the potential difference between B and D will be zero, just as we discussed earlier in the Wheatstones bridge. So similar to the case before, voltage along AB will be equal to the voltage along AD. And the potential drop along BC will be equal to the drop along DC. So if you do the calculations we did before, we'll end up with the same balance condition formula. R1 over R2 is equal to R3 over R4. Look at these two relations here. R3 is nothing but K times AD, while R4 is K times DC. So if you substitute this in our balance condition formula, we get R1 over R2 is equal to K times AD divided by K times DC. So if I cancel out the K terms from my numerator and my denominator, we get R1 over R2 is equal to AD over DC. So in a practical situation where I need to find out the resistance of any particular resistor, say R1, I simply connect it to a meter bridge with a known resistance R2. We then keep adjusting the position D of the galvanometer along the wire AC until no current flows through it and a balance condition is reached. Then we get R1 over R2 is equal to AD over DC, or my unknown resistance R1 will be equal to R2 times AD over DC.